Hello and welcome to the Components and Services Origins, Standards and Tools. This lecture is a part of the CI 7250 module, Software Architecture and Programming Models at Kingston University, and my name is Jarek Frankik. One of the learning outcomes of this session is to provide you with understanding of components and services from a point of view of a practitioner. This may somewhat overlap with the content provided to you over the last couple of days, but the point here is to present similar or even maybe the same concepts from a slightly different perspective. This will be followed with a review of examples of typical implementation of component technologies, service architectures, and web services. We will also have a practical session on Tuesday, based mostly on Google services. So, we will be talking about components, services, and web services. This is a monolith program. A monolith program is not a component or service technology of any kind. This is how programs looked like before components were introduced. To be precise, a monolith program could have had internal structure, could be, for example, an object-oriented program with objects, classes, and so on, units, and so on, but this internal structure was visible at the level of the source code of the program. Once the program was built, compiled, linked, and built, no internal structure, no clear internal structure could be visible. And this is how programs used to look like. A typical example of it is an executable file of a type exe in Windows or DOS system, or DLL, dynamic linked libraries. That was a monolith program. And then we had a breakthrough, and this breakthrough was a component-based program. Component-based program had distinguishable internal components, something that you could use separately from the program, something that you could replace by another component. So the difference between component-based program and a monolith program of the previous era was that in case of component program, we have components that we can locate after the program is built and delivered to the customer. Before I tell what a component technology is, I will tell you, maybe a bit untypically, what component technology is not. It's not a programming language, okay? Mostly because component technology is programming language independent. It's not any specific API or software library. It can be supported by software libraries, but it is not specifically an API. And it is also not an object-oriented technology. As I explained in the previous slide, you could have a monolith program, not a component-based program, which would be entirely object-oriented. So what component technology is? It is a methodology for linking software modules so that they can work together, communicate between them, and can be also dynamically interchanged. So this is a way to reuse software libraries that would be accessed and executed, performed, used in runtime rather than during the writing source code. And component technology is, or at least should be, a fully language-independent technology. Here is one of the formal definitions of software component provided by Klemens Szyperski in the last years of the previous century. So the component is a unit of composition with contextually specified interfaces and explicit context dependencies only. It can be deployed independently and is subject to third-party composition. Please note some key aspects of this definition. So first of all, this definition tells us that a component should have an interface. Interface is a kind of an agreement. We specify this component will provide this and these services, this and these functions to the world outside. It also talks about dependencies, okay, and independence. So independent deployment means that a component can be created, perhaps built, and then deployed to the customer in possibly a final binary compiled form ready to use. So it's not something that you would receive in the form of a source code and need to build. Another important definition of software component is a component is a non-trivial, nearly independent and replaceable, it's important, replaceable part of a system that fulfills a clear function in the context of a well-defined architecture. A component conforms to and provides the physical realization of a set of interfaces. And again, in this definition we have interfaces and we also have well-defined architecture. I will not go deeper into the topic of interfaces because it was covered in the previous sessions in past days. I will show you one more definition, which is probably my favorite one, even if it is a bit maybe not very technical. A component is an object in the tuxedo. That is a piece of software that is dressed to go out and interact with the world. And I think that's exactly what a component is. So, now when we are clear about what component and component technology is, let's have a quick view at, so this is component-based program. What is a service-based program or service consumer program? The concept here is nearly the same. Alright, sometimes it is difficult. What I mean is the boundary between component and service-based programs is vague, right? But the difference of paradigm between the two approaches is that we once again have a program. This program uses some kind of specific components, but these components are not an internal detail of this program. These components are somewhere outside in the world. So it's about distributing components, and if we have a well-distributed network of interacting and interconnected components, we can talk about services and service-based architecture. These are some characteristic features of service-oriented systems. So first of all, loosely coupled, so without many dependencies, allowing to work independently. Connected and communicating, self-contained, so separated and independent, making the complete logical system. Also scalable and open. In the opening part of this lecture I mentioned components, services and web services. The concept of a web service is quite simple. If a service is connected over HTTP, so the main protocol used in web connections, often via port 80 but not necessarily. So if this connection of a web service is provided over HTTP, it's a web service. So now we can continue into the overview of technologies, and we will start with component environments, namely 4 of them: CORBA, COM, .NET, and JavaBeans. Please note that COM is here introduced mostly for historical reasons. CORBA, and it's not a cobra. So CORBA stands for Common Object Request Broker Architecture. The central part of this name, the Object Request Broker, or ORB, or simply ORB, is the key part of this architecture, and it will be explained a little bit later. CORBA is a standard introduced by OMG. That's another acronym that doesn't mean what you might think. It stands for Object Management Group, an open non-profit standard setting consortium that is grouping more than 200 companies. This standard was introduced in 1991, which makes it historically the oldest, the first standard of that kind. CORBA is an interface for distributed objects, which may be implemented in different languages, so it's language independent, and running on different platforms, different computers, and different operating systems. CORBA is characterized by normalized semantics of method or function calls, and interfaces have to be specified in a special interface definition language, or IDL. There are standard mappings from IDL to a large group of languages, including C, C++, C++11, so a newer standard of C++, Java, Ada, Lisp, Ruby, Python, Smalltalk, COBOL, PLI, whatever you really want. There are also some non-standard mappings. However, it has to be stated here that some mappings are much more difficult than others. So, for example, Java and Python mappings come naturally, and they are particularly simple. So, the CORBA standard is actually the favorite one for Java and Python programmers. C++ mapping is notorious for being complex. There is some improvement with C++11, but still, even if formally CORBA is language independent, you can see here some clear preferences. So this is mostly platform for Java and Python, much less for C++. C mapping, so a non-object-oriented version of C exists, but it's very complex simply because you really need to model object orientation from scratch in this mapping, so it's basically impractical. This is the standard structure of CORBA. So basically all these environments, their purpose is to provide the means for communication between the client and server in an internetworked environment. So at the top of the structure we have client and server code, which is entirely user defined, so that's just the code that you are creating. And on the lowest level we have those earlier mentioned object request broker, the heart of the CORBA system. Object request brokers are vendor supplied modules of code, so they have to be written separately for each platform, for each operating system, and even for various language platforms, and they follow low-level CORBA standards to communicate across the network. And then between the user-defined, user-created content and vendor supplied code, we have some levels of code that is generated. So we get generators to create this code, and then this code can be built into a working binary. This is on the side of the client generated stub code. And object reference. Object reference is just a model of an object that looks like any other software object, but calling any function in this object reference will activate the stub code, and then will activate object request broker and actually the network of object request brokers, because your call from the client will actually be transmitted across the network to another orb, and through generated skeleton code it will run the object implementation located on the server side. A typical workflow for a CORBA project is first to create a CORBA compliant interface, which comes quite natural in Java and somewhat less natural in some other languages, followed by preparation of IDL definition, which is reasonably a simple step, and then this definition has to be compiled to the generated code. So input of such a compiler is IDL, and output is the source code in your selected programming language, and then this code has to be included into your final project. The next system that is only shown here for historic reasons, because it's hardly used at this moment, it's been replaced by something else that will be also discussed, is the Microsoft Corporation's Component Object Model, or simply COM. It was introduced just 2 years after CORBA, and because of the possession of Microsoft Corporation in the commercial ecosystem, it's proved to be very popular, mostly on the PC and Windows platforms. It's been grown from a previous technology called VB controls, or Visual Basic Controls, later based on C++ internal structure. So this system was particularly well integrated with VB and Microsoft's flavor of C++ called Visual C++. This solution was specific for Microsoft Windows. There were some limited implementation on other systems, but as I thought, they were limited. Like CORBA, actually it borrowed the IDL specification, interface specification from CORBA, and this specification IDL could have been used in COM, but it wasn't obligatory. And very much unlike CORBA, COM specifies binary interfaces. So actually any language, any platform that can generate an interface that conforms the binary standard of COM might be easily integrated into the ecosystem of COM. This made the platform available for any, well, supported language, particularly Visual Basic, which is not very popular anymore, and Visual C++. But unlike CORBA, COM was rather tricky for Java programmers, and to say that also Python programmers. Internal structure of COM was quite interesting. So first of all, local components. Local components were the technology, or is the technology, supporting distributed systems that are all sharing the same computer and the same memory space, so without process boundaries. So we have a client and we need to call something, a function on the server, which are actually together in the same system, but because we have one piece of software that calls a service from another piece of software, we can call the caller the client and the called side the server. And the COM defined a subunit on the client side which was called proxy, and another unit on the server side which was called stub. Actually is called stub. I'm using the past tense, but COM is not dead. It's not a past standard. It's still in a way alive, so I should use present tense here. Okay, anyway, if a client wants to talk to server, it actually talks to the proxy, which is a local representation of the server service, and the server obtains requests from the stub. And then we have a request broker, similar to an orb in CORBA system, which provides communication between proxy and stub. Now, if we want to repeat the same architecture for inter-process or inter-networking environment, so where the request has to be transmitted across an inter-process boundary and perhaps even across a network, so between various computers, we will have a similar structure to the structure of the local components, with one very important difference. So on the client side we have identical proxy, but we have additional client-side stub, and the stub is a part of the system which is provided by the component object model, so software developers don't have to provide a stub. And on the server side, the server obtains requests from a stub, but the stub is communicating with another proxy, additional proxy on the server side. So actually, as you can see, proxy, client-side proxy is mirrored on the server side, and server-side stub is mirrored on the client side. And the functionality provided by component object model is request broker that connects this client-side stub with server-side proxy. The powerful aspect of this architecture is that client is still communicating with a local proxy and server is still communicating with a local stub. So you don't need any modification to the binaries of neither client nor the server. You don't need to change anything in them. So the same module that works well in the local environment like this will be working well with the within the interprocessor internetworking structure like this one. Component object model was succeeded by .NET, introduced in 2002. This technology, though in decline, is still alive, however mostly in legacy systems. So it's still working in some Windows internals. Until recently it was the heart of DirectX technology, Microsoft's 3D graphics and gaming technology, and also Silverlight, which is now outdated. It was a .NET technology actually that used old-style ActiveX to run in non-Microsoft browsers. But what's now much more important is the new Microsoft approach called .NET Platform, and this is the current solution, so the current standard for Microsoft Platform. It's again specifically Microsoft, and it is a solution to problems component object model had with implementation of binary interfaces. So rather than forcing various platforms to implement uniform interfaces, let's make them running on the same virtual platform, so requests can be solved transparently by the platform as a native functionality. It's ultimately easy for developers because the model is like this. .NET Platform provides actually a virtual computing environment for all the processes running in this platform. These processes, various user processes, will communicate not with the native operating system, but will communicate with .NET Platform. And now all the request broking is a native functionality of this platform. So it's an ultimate simplification. This basically means that instead of finding the way to communicate between various platforms, we have one universal platform. The power of .NET is based on the fact that there is a range of languages built on top of .NET Platform, like C#, Visual Basic, F#, whatever. The difference is that it's not like you have a language and you have to provide some API to communicate with any particular platform. It's now the situation that you have to obtain a implementation of the language for the .NET Platform. But anyway, this is quite a rich environment with quite a good quality universal libraries, and also we have several different platforms based on the same basic principle. So .NET Framework is historically the oldest, and it provides websites, services, applications on Windows, and so on. A new, reasonably new framework which is called .NET Core, which is interesting because it's implemented on a range of various operating systems. So unlike .NET Framework, it's not limited to Windows. There are quite well-working implementation for Linux, macOS, and we also have Xamarin, which is basically a .NET for mobile platform. So as you can see, it's .NET is getting more and more of platform-independent solution. Let's have a closer look at this .NET Core platform. There is a popular misconception that this is something built on top of .NET Framework. It's actually not. It's more like a successor of .NET Framework. So .NET Core 1.0 is a replacement for .NET Framework 5, a new version. Okay, this new version is based on quite a different paradigm to the old style .NET Framework. First of all, it's a cross-platform or cross-system, and apart from Windows, it's provided for macOS and Linux. All substantial .NET technologies are now available in the core versions, for example ASP.NET Core. You can notice from this diagram that the versioning number has been reset with .NET Core. So what .NET Core really is, it's a free and open source, which is quite a revolution, because free and open source is not what you would normally associate with the Microsoft trademark. Maybe not in the past. It's more and more like this. Microsoft is now offering more and more free and open source solutions. It's a managed cross-platform software framework, successor of .NET instead of .NET 5.0. The current version is 3.1, released in December 2019. Looking quickly at all three of them, CORBA, COM, and .NET, CORBA, an open standard by OMG, a consortium of companies, had no binary interfaces. ORBs had to be delivered by vendors for each language implementation. IDL was a must, and it is still very popular among Java and Python developers. COM, unlike CORBA, specifies binary interfaces that must be implemented by every language supporting this platform. IDL is an option, may be used but it's not required, and the language is popular among C++ and VB developers on Windows platform. Note that VB developers are probably an extinct species. And .NET interfacing is a native function of the virtual machine platform, so there's no question of binary or non-binary interfaces. IDL is of no more use, and the platform is language agnostic, but C# is strongly promoted as the primary language. You will learn much more about Microsoft technologies and particularly .NET in the further part of this module. There's one more platform that I wanted to discuss here, and it's called JavaBeans. This is a set of conventions for Java to support component-based development. JavaBeans is specific because it's a Java-only component framework, so it doesn't comply to the request or expectation that a component-based technology would be language independent. This is language dependent, and all the support is embedded in Java language and supporting class libraries. But what's important and nice is that using Java native interface, Java classes, any Java class can wrap components built in other languages and also can become COM or CORBA components. Our next topic are remote services. I assume here a very broad and flexible definition of services because, for example, RPC is not technically a service, it's just an underlying technology that allows for remoteness in the actual component and service-based architectures. So this part of the lecture will rather look into the evolution of various techniques allowing for remote connections between various processes performed in various process spaces, various computers across networks, and so on. So we'll start with RPC, or Remote Procedure Call. One of the earliest inter-process communication standards started in 1980, so 40 years ago, by ARPANET. It precedes any kind of component-based architecture, not to even mention service-based architecture, because it started not as a part of any kind of components. It was just a method to call a procedure or a function in one place from another place. One of the first implementations was in 1981 in Xerox Courier system, and subsequently it was made popular by Sun in the Unix-based network file system. One interesting thing about RPC is that this system uses IDL. So IDL was not an invention by CORBA, COM. It is much older, and it started with remote procedure call. For us, the important point is that RPC is or was the basis for distributed services in CORBA, and also DCOM, so Microsoft Distributed Technology built on top of COM, Component Object Model. The sequence of operations during a remote procedure call reminds the one we have discussed for component object model, because one is simply based on the other. So first of all, client calls the client proxy, and this is a local procedure call. Then we have the process of so-called marshalling. The client stub packs parameters into a message format ready to be transferred across the network. An important aspect or issue of RPC marshalling is that the parameters or the data that is sent to the server side are packed into a binary package of data, as package defined in binary format. Then we have the client operating system, which is responsible for sending the package to the server, and the server operating system, which passes the package to the server stub. And in the server stub, we have the process opposite to marshalling, and it's called, not very surprisingly, unmarshalling, where the server stub unpacks the parameter from this binary package that it's received, and then the server stub calls the server procedure again as a local call. So important thing here is that the client thinks it just calls a local procedure, and the server in this step number 6 is called in the conditions that it looks like also another local call. So you don't have to specifically instantiate any kind of internetworking on neither on client or the server side. It's all working locally, and then the RPC infrastructure is responsible for transferring these or blocking these requests across processes or across the network. DCOM, or distributed COM, very briefly mentioned here mostly for historic reasons, was an RPC-based extension to COM, but it was rather infamous. The configuration was incredibly complex, scalability very limited, and the reason for that was mostly because RPC created binary packages to be sent across the network, and this is a very internet unfriendly security architecture. DCOM was operating on port 135, which had to be left open for binary transmissions, and this is actually a horror for any system admin. Basically, if you send binary data, you will never be absolutely sure what's in this data. So it's not a secure system, and for RPC to work across a network, this specified port 135 must be open, completely transparent for everything, so it's very vulnerable. And this technology had been fully replaced by .NET functionality. .NET introduced another approach, another system of sending requests across the network, and it's been called SOAP, Simple Object Access Protocol. SOAP, very much unlike anything RPC based, is HTTP friendly. And why is it HTTP friendly? Because it's a text-based format. So actually what you do, you send all the parameters of a function call coded in the text format. Text format, and actually XML coded format, is better because it can be analyzed and understood by firewalls and other network security devices. So we have here XML-based message format, XML-based configuration. Server functions are neatly exposed via XML-based WSDL specification. WSDL is that acronym WSDL, but instead of pronouncing this WSDL, we call it quickly WSDL. So a WSDL specification provides all the information necessary for the client to find bindings that will be then automatically generated on the basis of the WSDL specification. Pros and cons of SOAP. It's open, it's extendable, and it's most importantly internet and web friendly. Actually, SOAP requests are sent over HTTP, so the the fundamental web protocol, and they are quite often called or sent over port 80, so the same port that we normally use to access web pages. Cons, it's still a significant overhead, both in processing and transmission due to the nature of the text-based XML format, which is complicated. There are two more solutions that I would like to briefly present. Both of them are in Java universe. The first one, Apache Thrift, is an interface definition language and RPC framework originally developed for Facebook and currently developed as an independent open source project under a label of Apache. It's a complete stack for creating clients and servers with a lot of generated code and runtime library including protocol and transport layers. Apache Thrift provides a possibility for easy object serialization, very low overhead because all the data transmission is binary, but because it provides a very natural language binding for Java, and it is not a coincidence that it is developed under the label of Apache. Although it is a binary data transmission mode, it is still reasonably network friendly. First of all, this is a very clean library. There is no framework to code, no configuration, so it comes very naturally for Java programmers. And the other technology is Java RMI, or Remote Method Invocation, a Java-based object-oriented equivalent to RPC, supported for serialized Java objects, supporting distributed garbage collection, so quite interesting. RMI may incorporate API and an underlying protocol like Java Remote Method Protocol. The heart of this solution is RMI IIOP, so RMI over Internet Inter-Org Protocol, built over underlying CORBA structure. Let me now compare various data formats used in distributed systems. So we started with binary, which was fast and effective with no particular overheads, but it wasn't very internet friendly. I will just remind security problems with DCOM, which never proved to be, DCOM never proved to be really popular. A positive counterexample is Apache Thrift, based on binary protocol, but internet-friendly binary protocol. Binary was replaced subsequently by XML, which was internet-friendly, or which is internet-friendly because it's text format, easy to send over HTTP and even port 80, but it provides overheads in transmission, quite often complex configuration, complex encoding and decoding. And we also have not yet discussed post-XML formats such as JSON, YAML, text formats, but much simpler than XML. With this background, we can now proceed to the next big topic of this presentation, and these are web services. We will first of all discuss SOAP-based web services, and in particular ASP.NET services and WCF services, and then I will quickly characterize RESTful services quickly, because we will have a separate session devoted entirely to RESTful services. So, SOAP is a reasonably simple XML-based protocol for exchanging structured and type information on the web. It is an industry standard, lightweight as an XML-based protocol can be, and can support different protocols and formats such as HTTP, SMTP, MIME, and so on. It's based on the format of so-called SOAP message. The SOAP message format is based on a whole range of technologies. So first of all, we have a standard way to represent data, and this is XML based on XML schemas. A common extensible message format called simply SOAP, common extensible contract language, so a language describing interfaces provided by servers, and this is previously mentioned WSDL, Web Services Description Language. We have a way to discover site services, DCOM, and a way to discover service providers called UDDI, Universal Description Discovery and Integration. Now, the XML stands for Extensible Markup Language, and this is a language for describing documents with structured data. Industry standard designed to transport and store data, but what does it mean, language for describing documents with structured data? Let's have a look at an example. So, an XML document has to start with a header specifying its version, and then it consists of a number of tags. A tag can contain other tags. So here we have one big tag which is called note, and we have an opening tag and the closing tag. So the note starts here and ends here, and it contains several lower level pieces of information, fields, such as to, Tovi, from, Johnny, heading, reminder, and body, don't forget me this weekend. The important part here is that this is the user who defines what particular tags mean. So there is no such thing like a XML-based definition for the note or to, from, heading, body, and so on. It is all only sensible in the context of a given document. So XML does not do anything. You invent your own tags and specify what they mean. There is also a special format called XSD, XML schema, which is also XML based by itself, and this is a special language for describing data types. So in this case, this is like a description of the XML based description of the structure of another XML based file. WSDL or WSDL is an XML document describing web services. They define data types, they define messages in terms of those data types, they define bindings to transport protocol, message format, and they define services as collections of ports. So a port is in this case a function that you can remotely call. So WSDL describes all the services provided by a server. DCOM, document discovery. A client finds a particular web services by discovery. DCOM are the document discovering services at a particular URL. These documents are in XML format with DCOM or VS DCOM extensions. And finally, we have UDDI, which enables businesses to publish and discover information about who provides what services. It builds on HTTP, XML, and SOAP. In the universe of Microsoft, an original and ultimately popular web service technology based on SOAP was called ASP.NET. Web services meant that mean that functions can be called across the web, across the internet. Microsoft Visual Studio provides easy-to-use tools for generating client-side class bindings and skeleton code for the servers, complete with WSDL specification. So everything is made quite straightforward for developers who can create ASP.NET web services without much difficulty, but they are internally quite complex and provide much overhead. Currently, ASP.NET web services are phasing out and are being replaced by WCF. What is WCF? This is a part of so-called Microsoft post-2006 architecture that is based on three pillars: WWF, Windows Workflow Foundation; WPF, Windows Presentation Foundation; and WCF, Windows Communication Foundation. There are still SOAP-based services. They are still using WSDL, so there is no such a big change compared to ASP.NET web services, but there are some substantial behind-the-scene changes. The programming model, from the point of view of a software developer, is still very similar to that of ASP.NET web services. There's a lot of criticism about XML SOAP services such as WCF or older ASP.NET. First of all, these are transmission overheads, complexity of request infrastructure that are necessary to cover all flavors of RPC calls. Basically, you can look at SOAP as at a new version of RPC, which provides the equal functionality, but this functionality is put over the HTTP text-based or XML-based connection. There are also hardly any open interfaces in at least Microsoft-based SOAP services, but there is a big good point, and its flexibility. Remote calls are made nearly as easy as local ones. So all this complexity of the underlying infrastructure is transparent for developers. But it's still a complex infrastructure, and therefore there is another technology. So if we look at the evolution, we started from binary, which provided a lot of flexibility, a lot of efficiency, but it was binary and not very internet friendly. Then we had XML-based or text-based technologies, which were safe, which were internet friendly, but which were still quite complex. And now we have the third generation called REST. REST stands for Representational State Transfer. It was introduced by Roy Fielding in the year 2000. Sometimes you will find the word RESTful. RESTful means simply based on REST. RESTful services here will be only very briefly described because, as I mentioned, there is another session entirely devoted to RESTful services, which are currently absolutely trendy and very successful. Basically, RESTful services are based on a very dramatic change of a paradigm. Forget about RPC. RPC could have been transferring any potential remote call request, but it is not any longer the case with REST, because any kind of complex remote request is just dropped with RESTful services. So what's in place? Simplified semantics to express client requests. RESTful reduces all requests to 7 standard operations. Yes, 7, just 7 standard operations. So instead of full flexibility and one-to-one mapping from any kind of a function call to a, for example, SOAP request, we have something totally simplified, but RESTful model provides still a very powerful and quite a flexible model based on simplification, on a paradigm of a ultimate simplification of remote function call. In RESTful services, all transmission from the client to the server is performed using the URL address and 4 states available in the standard HTTP protocol. So an example of a RESTful request is shown here. Service.name.com is the name of the server, it's a URL of the server, and then we have something like account/trans/22.xml. This means that this particular request is about a series or collection of accounts. Within this collection of accounts, we choose the account with ID equal to 1, and for this account number 1, we are looking for a transaction with ID equal 22. And no other information is actually sent. Response is typically delivered in one of the following formats: HTML or XML or YAML or JSON. HTML is reserved for human interfaces, so if it is if the response is to be looked at or viewed or seen by a human, it will be HTML. And if it is a typical web service, so a piece of software remotely called by a remote client, it will be either XML or YAML or JSON. Web services will be covered in much more detail in the future sessions, giving us now time and opportunity to smoothly go to the final topic of this presentation: cloud systems. What is a cloud system? It's been introduced in the past sessions, so we will be now just briefly looking to some examples from companies like Amazon, Google, and Microsoft. So first of all, cloud systems can be further divided into IaaS, Infrastructure as a Service, PaaS, Platform as a Service, and SaaS, Software as a Service. And we will see examples of all 3 of them. One of the most important players in the area of cloud systems must be Amazon Web Services, AWS. As you know, Amazon.com is the world's largest online retailer with a revenue of $280 billion in 2019. And as such, it has to maintain a network of IT systems not only to support the average but also the peak customer demands. And the AWS, Amazon Web Services, takes what is essentially unused infrastructure and turns it into profitable business, creating the largest IaaS or infrastructure and platform as a service in the market today. The clients of AWS include NASA and Netflix, and the revenue just from AWS was $35 billion US, so it's quite a considerable part of the total Amazon business. Here you can see the market share of in terms of infrastructure and platform as a service, which clearly shows that Amazon AWS currently has the biggest market share. AWS is in fact a selection of web services such as Amazon EC2 Elastic Computing Cloud, which is basically providing a scalable virtual private server in the cloud, Amazon S3 Simple Storage System, Amazon SimpleDB, which is a structured data store, and Amazon RDS Relational Database Service, running MySQL, Informix, Oracle, or SQL Server. AWS is a global service subdivided into a number of regional divisions. Another example of a cloud system must be Google applications. What are Google applications? You probably perfectly well know. You use, hopefully, you use many of them. These are applications like YouTube, Google Maps, Google Play, Gmail, Google Drive, Google Calendar, and many, many more. Translate, Blogger, Photos. Alright? So, a question to my audience. Which type of cloud services is that? Infrastructure, platform, or software as a service? I hope this question is easy to answer. Google applications are not just the applications for the end users. These are also Google APIs, so gateways to use Google applications as typical web services called from other client web applications. For example, let's have a look at this link. You can try it using Google Chrome or Firefox. This is a URL link, so the only thing that we have to do is just to click it. But from this URL, we can easily read what kind of a web service request or web service call it is, and we can do it because this is a kind of a RESTful call. So everything that is important is encoded in this URL sequence. So first of all, this is a call to Google APIs, and the particular API that we are going to call is language/translate/v2, so version 2. So we will be calling version 2 of Google Translate application. And we have to provide a secret key, which for which you have to specifically apply with Google. But for example, for using Google Translate, these keys are free to use. The key, anyway, I make it secret because this is my personal key. Kingston University students who can directly access the PowerPoint version of this presentation can read this key easily. Apart from the key, we have the source language. It's a translation, so we have source language and target language. Source is English, target is French. We can specify a callback function that is not used in this example, and the query. The query is the word translate. So what I expect is that this particular Google Translate application will take the word translate and will translate it from English to French. So let's click on that and find out if it really does. As you can see, this is first of all JSON encoded, but JSON is reasonably easy for people to read. So we have the translated text with some data, and translations provided by the system contain the translated text traduire. This is French for translate. Another similar example is here. This is first of all, this is a very simple application making use of Google Web Service. So I can now type translate, click at the click me, and it provides translation traduire. But I can provide any other any other words, and this will be translated into French. We'll be looking into Google applications, and in particular the Google API's gateway to Google applications in more detail in the workshop. So now I will go to another example, Google Engine, and my very simple Hello World application, which was written in Python. And this application, it's not particularly interesting, it just displays the text Hello World on the screen. But what's important with Google Engine is that this is a service which allows developers to write a program in a range of programming languages, including Python, and run these programs remotely in the cloud. So again, the question for you, which will remain unanswered in this presentation: which type of cloud service is it? Infrastructure, platform, or software as a service? Finally, I would like to very briefly mention Microsoft Azure and Bing services. It's a brief not because they are not important, but simply because we will look into these services in much more detail in the further part of this course. But anyway, Microsoft provides service and platform and infrastructure as a service, so actually everything. These services are direct competitor to AWS and Google Engine, and they are fully supported from Visual Studio. We have to be aware that apart from the big three, Amazon, Google and Microsoft, we have a whole range of other, perhaps smaller, perhaps not so small, cloud services such as Heroku, a platform as a service for deploying applications written in several different languages, including Ruby, Java and Python. Very popular file hosting services such as Box, Dropbox, but also Microsoft OneDrive or Google Drive, iCloud, a file hosting system and backup system and photo streaming system available at iOS and Macs, and many more. This concludes our presentation. Thank you for watching, and I invite you to a face-to-face workshop session.